Hello and welcome everyone. I'm Akanksha Baid. I lead ads marketplace at Pinterest. I'd like to once again extend a very warm welcome to you for the third annual MADS Marketplace and Modeling Workshop. In this workshop, we aim to bring together practitioners and researchers working on ads targeting, ranking, and marketplace design with the goal to facilitate sharing of information and practices. As always, our overarching goal is to help strengthen the community and promote discussion on the most interesting and relevant topics in the ad space. Before we dive deeper into the agenda, I'd love to take a minute to thank and acknowledge our amazing organizers and presenters. Um, they've been working tirelessly behind the scenes to put this event together, so thank you very much. We'll move on to the agenda slide. Diving right in, we have an incredible line of speakers for you today from ads organizations across the industry to share their talks and their work with this audience. Each of the talks will be followed by a short Q&A session where we'll be accepting audience questions. So, we're looking forward to that. We hope you are too. Um, Going into the agenda, we'll be starting with a talk on personalization of ads by Instacart. This will be by Angadh and Xiaoming. Our second talk is from Pinterest Ads Modeling, where Yiping will be talking about user journey modeling. After a short lunch break, we'll go into a talk by Shobha Diwakar on YouTube ad recommendations, followed by another talk from Pinterest Ads from the marketplace team on challenges and opportunities in marketplace design. And our final talk will be from Snapchat on knowledge distillation in Snapchat by Joey Robinson. Finally, my colleague Sindhu Raghavan will deliver some closing remarks before we delve into 4 breakout sessions. We have a very interesting set of 4 breakout sessions for you today. These will be panel-style, casual Q&A sessions with Pinterest team members. We hope that you'll be able to stay on and join us there. Once again, I'm very excited to welcome all of you today, and I'm looking forward to a very interesting AMM workshop. Thank you. Jumping right in, our first talk is from Instacart. So I'd like to quickly introduce Angadh and Xiaoming from Instacart. Xiaoming is a machine learning engineer in the display ads quality team at Instacart, and Angadh is a staff machine learning engineer in the AQ team at Instacart. They'll be talking about personalization at Instacart. Please welcome Angadh and Xiaoming.
Thanks, Akanksha, for the introduction. Hi, everyone. Welcome to our talk today. Today, me and my colleague Angadh will cover the topic of personalizing ads on Instacart Marketplace. First slide. So a little bit about us. Instacart is a leading online grocery platform in North America. First of all, it is a four-sided marketplace between the consumers, shoppers, retailers, and food brands. So this leads to an interesting yet complicated problem domain for us, as all 4 moving parts need to be in perfect coordination to deliver a high-quality experience. Next slide. And in case you haven't tried it yet, this is typically how people do their grocery shopping at Instacart. So first, you type in your postal code, then you choose your favorite retailer and start to search and browse, build your basket. Then you place your order, pick it up, and or have it delivered at your doorstep in as little as 1 hour. Next slide. In terms of coverage and penetration, today Instacart is available to over 85% of US households and over 90% of Canadian households. And we partner with more than 700 national, regional, and local retailers to deliver from more than 65,000 stores across US and Canada. Next slide. So for example, we have partnered with some household names like Kroger or Costco in US or Loblaws in Canada. Next slide. And we are building our marketplace to be a one-stop shop for all the trip missions consumers are looking for. So beyond grocery, we are expanding our new verticals of non-grocery retailers. And we believe that this diverse retailer selection will be a key lever for consumer activation and retention. Next slide. So at Instacart, the consumer journey is different. It's not a spare fish shop, meaning the consumers search for one single item, add to cart, and then repeat. Instead, the consumers are doing more than just searching for one product and checking out. Uh, Instead, they walk in the virtual aisles, explore recipes and suggestions, and get inspirations, and build their full baskets. On average, they have around 17 to 20 items per order and shop for around 11 categories. Next slide. So finally, we come to the ads space. And this unique shopping journey allows us to build ads products that help advertisers to run a full funnel marketing strategy. So throughout the entire consumer shopping journey, from all the way from awareness to consideration and to purchase. To drive the awareness, we have things like storefront banners across the different categories to increase the brand reach and target new consumers with things like banners or emails. In terms of the consideration levels, they include display emails, and we can target complementary categories or target users who are likely to try their products or category, but haven't tried it yet. And for the intent levels, we have a display to retarget the lapsed consumers or target within the category or drive bigger baskets. For example, if you are buying shampoo, you may also intend to buy conditioner. And at the bottom of the funnel, we have sponsored products and savings to drive the purchase. They allow the brands, especially for the sponsored product, they allow brands to secure their shelf place across the Instacart marketplace on a cost per click basis. Next slide. And our existing ads products include sponsored product, display brand pages, coupons, and delivery promotions. For example, for now, we are creating more services for advertisers to house content and drive traffic to. For example, the brand pages, which is the third rectangle here, they are the dedicated pages for advertisers to store their branded content and also educate consumers about their product portfolio. And the brands will be able to drive traffic to these pages from their Instacart display or email campaigns. And all these ad products, they complement the sponsored product campaigns, which is our flagship as offering. And they strategically increase the campaign reach and impact when they are paired together. Then next slide. Then my colleague Angadh will take over and talk in detail about our work in personalization and how it helps in sponsored products.
Uh, Thanks a lot, Xiaoming, for that introduction. Hi, everyone. My name is Angadh. I'm going to specifically delve into sponsored products, motivate personalization, and then talk a little bit about how we personalize sponsored ads, then give it back to Xiaoming to discuss how we use personalization in display ads. Sponsored products. What are sponsored products essentially? Sponsored products are basically products that advertisers can place on various different surfaces, on top of the page or top of lists across various surfaces on Instacart, right? Here are some of the examples. On the search experience, advertisers can pay to basically have to show up on top of the search results page. And then basically customers can add these items directly to their cart. We also offer retargeting opportunities to brands where brands can basically promote their products on buy it again surfaces. Instacart customers are typically return customers who essentially repurchase a lot of their historical purchases. We also have several browse and recommendation surfaces across Instacart where we drive incremental purchases and conversions for our advertisers. We have a couple of different ways in which we serve them. We have inline placements where sponsor products are interspersed with products on surfaces, along with organic products that are naturally occurring there, um, which are a part of the surface. We also have dedicated carousels and surfaces which actually show on sponsored products. Most of us in this room are actually familiar with this funnel, but I'll go through it in some detail anyway. This is essentially an end-to-end summary of how sponsored products are served at Instacart for various different surfaces. We search, browse, and so on and so forth. But generically speaking, it's the funnel kind of like is similar for all surfaces. We get a request from the client, which provides us with the user who's shopping, and the context in which they're basically sponsored ads are expected to be presented. Once the request is received on the server, we have a retrieval stage, which uses a recall model to fetch a large set of candidates, which are the most promising and which are the most relevant to the given context. These relatively large candidate set is then basically passed to the next stage, where we have a lightweight machine learning model that does first pass ranking and filters or distills down the candidates to the most promising one, say a few hundred. Then these are basically sent to the next stage, where we actually use a heavier machine learning model to predict relatively accurate probability of conversions and clicks and so on. And then these PCTRs are then fed to the auction. That's the next stage. The auction uses the PCTRs from the previous stage and the bids, and this is where the winning ads are decided. We use a second price auction, which is then used to rank as well as price these ads. After the auction stage, the ads are sent to the client, which then decides how to basically render them, as we discussed a few formats previously. Last but not the least, we have extensive server-side logging and client-side logging. We log everything that happens in this funnel on the server side, as well as actions taken by the user. What ads did they see? What did they convert? What did they add to cart? And so on and so forth. And this slide is essentially just a summary of what I just spoke about in the previous one. With this slide, I'd like to actually motivate the case for personalization a little bit. This basically shows a user who's looking for bread in Safeway, and the top of their search results page is filled with relatively relevant and good ads, right? But if you don't realize that this user has been sort of an Instacart member for a very long time and they've never purchased non-gluten-free products, you would actually be showing sort of ads that the user is never going to engage with. This is sort of like inefficient use of ad slots. This problem is actually even worse for recommendation surfaces where the intent of the user is not particularly clear. Having motivated personalization in sponsored ads, let's talk a little bit about what personalization at Instacart really entails. Right? Some preliminaries. I want to call out what we actually intended to build with the personalization algorithm. We wanted to build a first pass general mechanism to sort an entire catalog. So that technically means we should be able to sort a store with, let's say, 100,000 items. And the goal here is not to, build, let's say, like predict what exactly the user is going to buy right now. Like, it's not a contextual ranker that's optimized for a specific surface. And we're also not looking to predict like calibrated purchase probabilities or CTRs. What we expect is the ability to rank a catalog and do that with sort of like relatively low latency. Right? Before we dive into the model, some data characteristics that need to be called out. We typically see users shop for baskets, and users don't really shop equally from all categories. So you could basically buy a lot more produce than household items like, I don't know, garbage bags and so on. There's also, if you follow the user journey in time, you'll also realize that people shop for bananas more often than garbage bags. What that ends up doing is that there is a popularity distribution and a skew in the data, in the training data that's used to actually train the model. There's other quirkiness where, most of our users actually do end up shopping for their household and have a comprehensive basket. But there are one-off orders where somebody could order 10 bottles of vodka, or somebody buys 20 bags of pet food. So and it's really hard to say a whole lot about that user. Not going into detail about the feature summary here. We do extensive logging of user actions and user action histories, users inputs. We have some aggregate user behaviors. And on the product side, we have catalog features as well as product popularities. Well, since I called out that we want to build a ranker that is able to rank the entire catalog, we've decided to basically first build a content-based embeddings model. And what we're doing here is essentially learning a language model internally. Content-based embeddings is a fancy word basically just for a language model. And we changed this word to work on over 1 billion search conversion logs. And the output of this algorithm is basically word embedding for each of the word in the Instacart vocabulary. We use these to generate pre-trained representations for products, search terms, and other taxonomic entities like files and departments, etc. That being said, now these pre-trained embeddings serve as inputs to the next stage. And the next stage is essentially a two-tower model. I hate to use that name, but yeah, it's a two-tower model with a user tower and a product tower. A user tower essentially has inputs like product history, search history, and a bunch of other user signals, which are then passed through several layers of densely connected neural networks. And then what we end up at the end is a user embedding. Same thing on the product side, product descriptions, catalog memberships, and other popularity info. Signals are then passed through multiple layers. And at the end, we have distilled down to a product embedding. We do a dot product and predict the probability of purchase. We have positive examples from the purchase data of the user. The negatives are essentially sampled from a couple of different sources. We have random candidates that are picked randomly from the catalog. We also sampled from the popularity distribution. The question of why did we use this particular structure? Well, it's the ease of scoring and the ease of serving. Right? We essentially just cut this model into two different halves. We have the user half and the product half. We score on a regular cadence and generate user embeddings and product embeddings on a regular cadence separately. And then all that's left to do is basically just do dot products really fast during serving. Right? We do that using a sharded Postgres database and sort of like built-in functions. And we do that because these are co-located, or these artifacts are co-located with other catalog data, which enables us to do like all of the backend jobs in one place with a relatively low latency. Some of the takeaways from this exercise, evaluation is kind of challenging because, I mean, if you rank an entire catalog of 100,000 items, the user is not going through these in one by one and giving you feedback. It's several different services, and there's heterogeneity of the user experience, which makes it hard for us to correlate an offline metric with an online metric. In the end, we did go with recall of novel purchases versus catalog depth. Novel purchases being items or products that the users never purchased before. Cold start, I think I called this before. New users who basically just buy one coffee machine we can't really have a relatively good representation for those users. Since we're sampling both from random distribution as well as like a popularity distribution, we can actually change the proportions of negatives that come from each of these and then sort of like adjust for popularity. One thing we realized was it's hard to actually control the exact amount of popularity by doing that. So instead, we just did sort of like 50-50 from popular versus random, and introduced popularity externally. Another thing is around retraining. Instacart is constantly growing. We launch new partners and new verticals all the time. And launching a new vertical means updated language. So we have to update our language model, which then necessitates, update of every other model that actually uses it. A couple of different applications. One place that we use personalization directly is retrieval of ad candidates in browse experience, right? Where the intent of the user is not very clear and the candidate size is relatively large, right? In search, when the user is looking for organic orange juice, they're telling you exactly what they need. But in the absence of a very strong intent, personalization serves as one of the strongest signals with which we perform retrieval. And for later phases in CTR prediction, there's a couple of ways in which we actually use personalization for browse and recommendation surfaces, which are several different surfaces with varying context and product relationships. We have several different models that predict these CTRs, and personalization score is used as an input feature in tree-based XGBoost models. For search, which is relatively contained experience, we have a wide and deep model architecture. The embeddings from the personalization algorithms are then used directly to initialize the user embeddings layer in the deep tower. There's another way we actually try to learn, or personalize and learn user representations from the search sponsored logs themselves directly. The problem with that was we didn't have visibility into data that's outside of sponsored product logs. And that's, even though ad conversions represent a significant chunk, it's still far fewer. It's still not comprehensively covers all of users' actions in the past. With that, I hand it over to Xiaoming to talk about display ads.
Thanks, Angadh. So now I will continue to talk about how personalization could help on other aspects of our ads offering, in particular, the user targeting for display ads campaigns. Next slide. The next one. Okay, thanks. So on display side, we provide advertisers with audience targeting levers. They could be purchase-based or other customized audience. So the advertisers could unlock sales by showing display banners to the right audience. So on the right side of this slide deck shows a search keyword banner. And these display banners, they are auction-based ads. They enable brands to promote engaging, targeted, and creative contents to consumers. They can be placed across the different discovery surfaces, from keyword search to browsing, storefronts, departments, and aisles on Instacart. And display ads also equip brands to reach new customers with customized targeting that is based on anonymized purchase behavior or some specific keywords. Next slide. So personalization in this case will help in our user targeting feature where the advertisers specify a manual targeting segment and we select users within that segment that maximizes attributed sales. So the experience will look like for the experience advertisers when they create display ads campaigns at Ads Manager, which is our Instacart ads platform. They will provide a few constraints, including the menu segment rules from the list we provide, and set the budget limit and controls the CPM bid in their campaign. Meanwhile, our ML targeting model will work in the background to help select the audience within the constraints to optimize the campaign objectives. And on the consumer side, when they are shopping at Instacart, they will be exposed to brands and products that they are more likely to be interested in, and thus have a more streamlined shopping experience. Next slide. So here I will walk you through the personalization workflow in user targeting campaigns. So we take the user embedding and the product embedding from the last dense layer of the two-tower model that Angadh just introduced earlier. And we combine them with more user-side features, including their interactions with app, like the purchases and stuff, and campaign-side features like the product metadata and the ad group's creative metadata. Then we train a downstream model to power the audience optimization in a display campaign. And our model is optimized towards maximizing sales. This is achieved by predicting the most likely to engage customers. We also have the ad spend as a counter metric, and this part is taken care by adjusting the ML threshold by looking back the option and the impression data from the past period of time. Next slide. So here's a few takeaways from our personalization use case. So first, the personalization embeddings, they provide a strong signal for user affinity, even with the absence of campaign-related purchase history. And also by training a downstream model, we could effectively calibrate the prediction scores across users. So it is valid for us to apply it in user targeting. Also, in the targeting scenario, we need to deal with a wide range of features from both the user side and campaign side. And although the cross features that could be learned in an implicit manner, we still benefit a lot by leveraging the domain knowledge to focus on interactions that work. And we found that the explicit feature interaction constraints play an important role for robust model performance. And if we guide the encoding for non-linearity, we can greatly improve the predictive power and have less noise and better generalization. Also, through our experiment, we are able to observe lift on the both new and returning consumers, and in line with our optimization objectives. So now we are working to build more insertion signal to reflect the user interest change or intent change in a more real-time manner, and also building our streaming infra to support serving on these new features. Next slide. So for both the display ads or sponsored product ads, we share some generic challenges across different formats, although they apply slightly in slightly different context. For example, in terms of the sparsity, when we are looking at the top funnel events, they are sparse in terms of both the context and conversion. The context could be sparse for different like search keywords or browse context, and the sparse in conversion also leads to the label imbalance problem. And also things like when it comes to core modeling for display ads, the attribution is a non-trivial problem to measure the treatment effects. And also in terms of code start, the display as suffers more about the code start in terms of the user side instead of this product or campaign side. So Angadh, would you like to chime in and talk about the challenges on the sponsored product side?
Yeah, I mean, sparsely, let's say we have tens of millions of users, and at some point we realize using them as categorical features, it's overfitting pretty quickly. In fact, like we see, we at some point we were seeing our validation error actually increasing after the first epoch. There's label imbalance, obviously, which is sort of addressed by downsampling the negatives in a random phase, in a randomized manner, and then sort of upsampling or like basically correcting the scores when you're serving. There's also like the question of should we use clicks and conversions because typically Instacart customers are returning and then they sort of repeatedly shop the items. So should we use something as a click or a conversion right now, or basically just a lifetime value of a particular ad impression that's clicked on? There's also other challenges. For example, we have selection and position bias. We have exploration. We actually do randomize a certain portion of our traffic and then essentially use that for transfer learning as well as sort of like validation. And we have several sort of issues in cold start, right? So for example, for new users, which represent a significant portion of our traffic because we are growing, we have incremental training where we basically, we keep what we learned until the previous training run and then sort of like use that to start or sort of basically initialize the parameters for the model training on the next given day. We have issues with product and advertisers cold start. So if you use signals that are basically computed from historical engagement, they're very likely to basically be not promote or like be inaccurate in predicting CTRs for new products. In addition, there's also like new surfaces because we're constantly sort of launching new different surfaces on which we source sponsored products, and we don't have click logs from those surfaces. It's really hard to start sort of like cold start a particular surface, right? So in that case, we basically have to use a sort of like a back off model. And then eventually when we have enough impressions and clicks, we basically train a model that's specific to that surface. With that, we come to an end and I'd like to take any questions from the audience.
Thank you so much for that very interesting talk. I certainly learned a lot. I'm going to be moderating the questions that the audience has been posing for Angadh and Xiaoming. There's been quite a flurry of questions, so I'll try to get to as many as we can. I think the first question is, how do you manage the personalization model retain promote cycle?
Yeah, I mean, for the longest time, we actually like had these fixed, but then, as we keep launching new verticals and we keep updating our language model, we actually needed to basically update and retrain models. I mean, this is basically maintained by, you move on. I mean, so there's two questions, right? Like, there are places where the distribution of scores matter, and then there are places where the distribution of scores don't matter as much. Right? So for places where you want to, for places where like organic surfaces where only the ranking matters, you can basically move on from one version to the next and then experiment. And then let's say if that wins out, if that does better than the previous version, you basically roll it out, right? But for places where you need, when you use personalization as an input and the distribution of the input features changes and that affects your sort of like model performance over a period of time, you essentially freeze the scores to come from a version that was trained on a certain date, and then sort of like uh, only perform retraining on the newer versions that were trained, and sort of like we'll have to do it like and then experiment online, uh, sort of, and then move from one version to the next.
I see. Great. Let's jump into the second question. So, how is relevance to the user context determined used at the retrieval stage? Do you have models that primarily optimize for engagement? Are they using human labels? Is it traditional IR tech? What do you do?
Yeah, I mean that's a really interesting question, right? So the question here is there's there's many different contexts, right? So we have surface. I mean, let's pick search, right? In search, the query that the users sort of like given you is presents the strongest intent. So you want to make sure that the results that you're retrieving are relatively relevant to the search query. We do expanded keyword matching. We have sort of like semantic neighbors where we use some sort of a language model and then use the embeddings to basically pick out what products are the most relevant to the search query. And I mean, given the large set of candidates, we probably could do sort of like I mean, we don't do this but currently in the retrieval stage, but in the first pass stage, the relevance to the search query and then sort of the personalization score to that particular user is used as, in a weighted manner to basically then kind of weigh relevance versus personalization, right? Versus and sort of like relevance is also kind of interesting here, right? Like there's one thing is to predict a click-through rate for an ad in the context of a query, and the other thing is the relevance of that product to that query itself. So relevance is sort of like we also have an independent sort of model that predicts the relevance of a query product to a query, and that is trained on human judgment. So basically, we have human raters who basically are given query product pairs, and they give their feedback on those. And the relevance model, independent of CTR, basically predicts the relevance, and then we use relevance to form to promote or demote ads in a given auction.
I
So
see.
it's a little bit of both.
Makes sense. Makes sense. Let's move on to the next question. So, how do you blend organic search versus ads content? Because arguably, in the top case, especially when you're showing ads in the feed, how do you actually go about blending them? How closely do you work with the organic portion of things?
I mean that it's a great question. I mean it's obviously a challenge, sort of mixing too many ads, especially too many irrelevant ads, actually reduces the quality of both organic search. That ends up in reduced basket sizes, reduced conversions, and so on and so forth. It's a bad user experience. So, I mean, like I mentioned, we have specifically for organic search, right? We have a relevance model that predicts the relevance of the products to a given search term, and then based on those relevant scores, the ads that were retrieved, ranked, and the final set of candidates, and then basically you weigh the relevance as and then figure and based on if you have, let's say, a significant number of relevant ads, then you're likely to show an increased ad loads at the top versus let's say you don't have a lot of great ads or highly relevant ads to a particular search term, then you want to sort of like disperse them lower down the list and so on and so forth. So I mean, not talking to the exact mechanisms, but I mean, there's sort of like the relevance portion then that kind of optimizes for how many ads do we show in the top, or how many ads, how do we spread them out in the list. We start with a fixed format. I mean, we have fixed formats for several places, several placements and pages in browse, but for search, we change the number of ads we show on top based on relevance.
Makes sense. And like, I mean, these questions are in the Instacart context, but a lot of these are like very pertinent to like so many of our ads products. So it's quite interesting how you guys tackle these. I'll move on to the last question, maybe the fourth question. Maybe we have time for one more. How do you evaluate the effectiveness of first pass filtering?
That's a great question. I mean, the only way that you have right now, I mean, we essentially haven't. I mean, one thing to basically say is that like the challenge here is any change that you make here is then basically there are a couple of different changes downstream that are then basically modifying the effect of your first pass filtering. Uh, we've had sort of, I mean, there are specific metrics that you can take a look at that then basically can talk to the effectiveness of first pass filtering, but this is something that we're still sort of like, still grappling with, right? We're still sort of like we're in the beginning phases of actually implementing first pass filtering, and this is something that's still sort of like an open challenge for us.
That takes us to our last question of the day. Last question of this talk. So, in the context of a two-tower model, are negatives sampled from the impressed ads or all ad candidates at that stage of the funnel?
Okay, so I think I probably did not. I wasn't very clear. The two-tower model, right? The personalization model is sort of independent of ads. It basically has all purchases made by the users across all surfaces. So this is sort of like this is not an ad-specific model. So we consider, so it's basically just building a user profile using all history that it has available to it. So it's independent of the ad context, right? And the negatives that are sampled are essentially sampled from the entire catalog of the store where the user actually placed the order.
See, it's super helpful. Thank you so much for a great talk and for answering our questions. Thank you so much for coming.
Right. Thank you. Thanks a lot.
We'll jump right into introducing our next speaker. Our next speaker is Yiping. She's in the ads ranking team at Pinterest, and she will be talking about user journey modeling. Okay.
Thank you, Akanksha, for the introduction. Yeah, good morning, everyone. My name is Yiping. I'm a machine learning engineer working on ads ranking team at Pinterest. So it's my pleasure to be here. And in this talk, I'm gonna share some practical experience and lessons we have learned from user journey modeling for Pinterest ads ranking. So Pinterest is a visual discovery engine, and the mission of Pinterest is to bring everyone the inspiration to create a lively love. And as for the ads team, our goal is to deliver promoted content that is also valuable to our users. The responsibility of ads ranking at Pinterest is in the middle of the ads delivery funnel. For those candidates that are selected from the retrieval stage, the ads ranking model predicts user engagement, like the probability of the user to click the pin, save the pin, or hide the pin. And this prediction will be used in later stage for computing utility and select auction winner. And here is a quick recap of how the Pinterest ads ranking model structure has been evolved. In the very beginning, the team developed logistic regression to predict ads engagement. And later on, the model was migrated to a classic hybrid structure that combines gradient boost decision tree and logistic regression. And with the recent rise of the deep learning techniques, the ads ranking model also evolved into YM deep neural network. However, as the company grew and the system complexity also grew in the same time, we have different service in Pinterest, different product types, different ads format, and we found training and tuning a model for each of these different types and housekeeping all this model together gradually becomes a challenging and tedious work. So we built AutoML. It's our in-house deep learning framework that automates feature preprocessing, feature crossing, and it also provides flexible model structure using some state-of-the-art machine learning techniques so that we can reduce some efforts for feature engineering and model tuning. And we also adopt multi-task learning in order to simplify our system by reducing the number of the models. And last but not least, in the past 1 year, the team has been focusing on user journey modeling. So the goal of user journey modeling is to serve personalized ads to our user by understanding their journey in Pinterest app across not only organic contents but also promoted contents, so that we can introduce valuable products to our user and further bring them from inspiration to action. So we want to build an ads ranking model and corresponding infrastructure that is able to capture such latent interest behind the user engagement history. So first, let me briefly introduce the baseline. Here is an overview of the ads ranking model that we launched in 2020. This model will first preprocess the input signals by performing embedding lookup, normalization, feature crossing, and then followed by several fully connected layers. On top of the fully connected layers, we have multi-tower structure to handle different product type in Pinterest. Using this multi-tower structure can help to isolate the interference between different product types without hurting each other. And in addition, this model jointly optimizes different objectives like click-through rate and other engagement action like good click and scroll up. This multitask and multi-tower structure not only show better performance compared to a single task and single tower model, it also allows us to simplify the system and save infrastructure costs for Pinterest. We don't have time to cover more details for this baseline model, but please feel free to check our engineering blog on Medium. And as I just mentioned, we want to build an ads ranking model that is able to capture the user interest behind their engagement history. So we want to add something new on top of this model. And here is what we proposed. We first collect user engagement history from Pinterest log and transform the data into sequence of features. We build a new subnetwork to learn from these sequence features, and I will talk about the structure of this network later. The output of this network will be a representation of user interest, and it will be passed directly to the fully connected layer. This user journey network is co-trained together to optimize the objectives for the ads engagement. In the first phase of this work, we focus on user short-term interests. So we collect user most recent engagement events in the past few days, and each event is represented by a high-dimensional embedding. The first idea we tried is attention mechanism. For those who are not familiar with attention, we can use this simple example to understand the idea. On the right-hand side, we have target ad about recipe of cake, and on the left-hand side, we have a sequence of user engaged pins. So given the context from the target ad, which is about a recipe of a cake, those engaged pins that have similar topic like dessert, food, or recipe should receive a higher score. That means we want to put more attention on these engaged pins that are related to the target ad, while other irrelevant pins about home decoration should receive a lower scores. So this is how the attention-based network looks like. Now we have user engaged pin, we have target ad. Both of them are represented by high-dimensional embeddings. So for each individual user engaged pin, there is a activation unit that will take the embedding for this pin and the embedding for the target ad to compute an attention score. As we discussed in the previous slide, this attention score reflects the relevance between the engaged pin and target ad. So all these attention scores will be used later to compute a weighted sampling over all the user engaged pins. So with the different scores for different engaged pins, the model will put more attention on the pin with higher scores. So the final output of the weighted sampling will be a representation of user interest. And it will be concatenated together with the embedding of the target ad and passed to the original ads ranking model. We have explored different choices of activation units. It can be a very simple similarity function, or a more complex activation can be like first having the two embedding cross by different crossing strategies, like element-wise differential or maybe element-wise production, and apply multi-layer perceptron on top of this the crossing outputs and the embedding itself. So in the exploration of choosing all these different activation functions, we found that a model with a more complex activation units will converge slower. However, if we use a well-pre-trained embedding to represent both the pin and the ads, the two relevance embedding are already close in the embedding space. In that case, using a simple similarity function is pretty effective. Another model choices we found particularly helpful is applying additional transforms on top of the original feature representation. The motivation is that we found if we use simple similarity function together with the fixed pre-trained embedding, the entire activation function becomes a constant. There is nothing we can optimize here. So we add linear transforms on top of the both engaged pins and target ad to make this network optimizable and also tunable during training. This also allows us to control the output dimension of this attention network, which will also affect the numbers of parameters in the original ads ranking model. And in our offline evaluation results shows that the model performance is boosted with this additional linear transforms. So with this attention network, we saw significant improvement for AUC and loss in our offline evaluation. And online A/B testing also showed very exciting result. We saw consistent and significant CTR improvement in the day-by-day comparison. We even saw non-trivial gain on the Pinterest revenue. Right now, this network is serving major traffic for Pinterest ads. In the same time, we are thinking about more improvements on the attention network. How about we use more user events to represent the user journey? Also, in the first phase, only one high-dimensional embedding feature is used. How about we use more features to represent the events? Also, the attention network does not consider timestamp or the order of the user events. What about we build a time-aware network? So with these ideas in our mind, moving to phase 2 of this work, we first collected hundreds of events for each user in the past few months. We have built an offline batching process that parses user events from the Pinterest latest log every day and materialize the events with a predefined feature set. Here, each event is represented by categorical features and also timestamp features. And then the process will aggregate the events by user and produce a sequence of user actions sorted by timestamp. The process will merge the latest sequence with the old sequence that was generated from the previous snapshot. So the final output is aggregated from a long lookback. 'back' 'window. 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 'back' For the second version of user journey network, we build transformer to learn from a sequence of user events. For each event, the model will first learn embedding for the categorical features and also generate positional embedding from timestamp features. All the embeddings for a given event will be combined together and passed to the transformer. The transformer part is a typical transformer encoder. It has multi-half cell attention layer and followed by residual connection and layer normalization. After that, a point-wise feed-forward network is applied, and then finally again the residual connection and the layer normalization. On top of the transformer encoder, there is another multi-layer perceptron, and the final output of this network again will be passed to the fully connected layer of the original S ranking model. One important component of transformer is using positional embedding to inject information about the order of the sequence. Here, the position of the event is represented by the timestamp feature of the event. Also, we bucketize the timestamp feature into discrete position. We have tried different approaches to generate a positional embedding. A simple way is to use the sine-cosine function to generate a static encoding, which is proposed together with transformer in the paper Attention is All You Need. Positional encoding is originally designed for machine translation so that the tokens in the sentence will be closer to each other, not only based on their meaning, but also based on their position inside the sentence. Another approach we try is to let the model learn an embedding matrix for this position index and then use that position to look up a positional embedding from this matrix. And it turns out having a learnable positional embedding has better performance in our scenario. In addition to the transformer, we also implement a two-layer gated recurrent neural network on the same set of sequence features. And in our offline evaluation, the GRU network slightly outperformed the transformer. So we once considered to run online experiment with the GRU network. But later in our benchmark, we found that the latency and CPU cost for this GRU network is significantly higher. So given a trade-off between the model quality and model cost, we decided to choose the transformer instead. But we do believe that this does not necessarily mean that the transformer is not as good as GRU. Since we only compare with a vanilla version of transformer encoder, we believe there is still room to improve the network structure as well as the loss function. We also try to measure how the freshness of user events can impact the model performance. We simulate the delay on user events in offline and compare the model that are trained with different level of delay. And the result shows that the real timeliness of user events really matters. But still, it's worth to mention that even the model trained with delay events, the performance is still better than the baseline. So given the fact that the freshness of user events is important, we build an infrastructure to the Pinterest user signal service in order to gather both long-term events and real-time events. On the left-hand side, we have offline continuous process to generate both kinds of events. For long-term events, as we mentioned, we have batch process that aggregates user events in a loopback window, and we daily upload a dataset into a batch sequence database. This batch sequence database contains hundreds of events for each user, and the freshness of the contents is at least 1 day old. For real-time events, we use Kafka Stream to listen to the Pinterest front-end events, and then upload the real-time events to a key value store. The key value store contains all the real-time user events in the past few days, and the data freshness is usually seconds to several minutes. So during the request time, when a user comes in, a sequence event handler will retrieve both long-term and real-time events and aggregate all of the events together. The aggregation is based on the timestamp of each event, and we also make sure there is no duplication inside the aggregated sequence. After the aggregation, the handler will return the real-time sequence into our ads serving system and serve this real-time sequence with the transformer-based network. And here's a result of the transformer with the real-time events. Compared to our first version, in offline, we saw both AUC and loss are further improved. And in our A/B testing, the result again show very, very promising gain in the ads engagement metrics. And that's the end of this talk. And I want to take a moment to thank all the contributors who made this work happen, including my teammates in ads team and also our beloved partners in ML infra team, serving team, and platform team. And finally, want to thank every one of you here for listening to this talk.
Hi, everyone. My name is Islam Al-Araj. I am an engineering manager in the Ads Retrieval team, and I'll be moderating the next few sessions. First, I'd like to thank Yiping for the insightful talk on user journey modeling, and now we can move on to a Q&A session on the topic.
Sounds great.
So our first question is, so during the model development, how do using different sequence length affect the model's performance?
Yeah, so the length of a sequence is one of the tunable parameters. We have tried a trend model with different sequence length. And actually, as expected, increasing the max sequence length also increased the evaluation metrics. However, if we further increase the length to a larger value, the gain is diminishing. Also, serving this transformer encoder, we found in our benchmark for our online experiment, we found serving this transformer encoder introduced non-trivial extra infrastructure costs and latency. And so I would say if you want to if you want to use a longer sequence length, you need to consider the trade-off between the model cost and the model quality.
I see. All right. Our next question is, so did you try temporal CNN given that the cost, latency, and generalization requirements for the model?
Yeah, so that's a good question. We haven't tried any approach that are related to CNN.
Okay. So our next question is about model serving. So with the transformer model, how do you serve this online? Like, what are the biggest challenges to serving an online transformer model?
Yeah, I would say the most challenging part of this entire work is the serving side. So for model serving, we need to handle the extra serving costs and latency that is introduced by this complex model. Unfortunately, we have some experts in the team to benchmark and optimize the serving performance, like compiling the library that is optimized for deep learning operations. And I would say this is definitely not an easy work. And also, feature serving is another challenging task because it's very hard to serve a long sequence, especially if you use high dimensional features. Because the network bandwidth for fetching this long sequence would be an issue, and also logging size will increase quite a lot to get with this sequence features.
I see. So in the presentation, you mentioned that during experimentation, the GRU model showed a slight performance improvement over the transformer model. So have you tried stacking multiple transformer and see if this would outperform the GRU? There's definitely challenges, as you mentioned, with latency, but in terms of performance, have you tried this?
Yeah. So stacking more transformer encoder definitely improve the evaluation metrics because I think overall more parameters almost always leads to better results. But yeah, as we just discussed, this again would be the trade-off between if you can tolerate such additional cost to your serving system.
Got it. All right. Going back to the sequence lengths that used in the model. So one challenge with training sequential models when on user actions in general is how to prevent label leakage. So how did you handle this for your model?
Oh, you mean the label leaking?
Yeah.
Okay. So yeah, label leaking is definitely one of the potential issue that we need to be careful. We don't want a model to cheat by looking at the events in the future. So I think this will depend on how you collect your sequence and how you combine the sequence with your training data. But I think one tip is that you can use the timestamp of the training data to filter your sequence, so that any events that has larger timestamp than the ads, then you can drop those events so that you can guarantee there is no future events for this specific ads.
Got it. So we have another follow-up questions regarding the sequence length. So you mentioned that as you experimented with different sequence lengths, there's a performance increase until it stagnates at some point and starts dropping. So what turned out to be like the ideal sequence length, and why do you think model performance drops after a particular point?
Yeah, I think I cannot reveal the actual number here, but I would say in our experiment, several hundred of a sequence length is a reasonable number. But if you want to try even more high dimensional embeddings in your sequence, then you will probably don't want to try more than 100, because that will significantly increase the challenging, significantly increase the training throughput, not only in training but also in serving.
Got it. Got it. So throughout the development of the experimentation, like how long did it take to conduct an end-to-end A/B test or like an A/B experiment? And do you do it on the same environment?
Yeah, so basically what we does is to have an extra subnetwork to our S ranking model. So conducting the so having the model train and conduct A/B testing usually takes about 3 weeks in Pinterest. But however, preparing the data and also preparing the infrastructure definitely take more time. I would say it would take several months to get this done.
All right. So we have one last question. It says, have you tried any linear complexity transformer variant?
Linear complexity transformer, no. So yeah, right now, well, transformer is still the vanilla version of transformer. Yes, and definitely the team is looking to improve the network structure, and also some other workstream in Pinterest also prove that having a well-designed loss function to supervise the learning inside the transformer is also a effective way to improve the transformer performance.
All right, perfect. Thank you so much, Yiping, for answering the questions. And at this point, I think everybody's hungry, so we're going to take a 30-minute lunch break. After the break, we're going to have upcoming talks from YouTube, Pinterest, and Snap, along with the various breakout sessions. So hope to see everybody in 30 minutes. Everyone, welcome back. It's Islam here again. I hope you enjoyed your lunch. I'm happy to introduce our next speaker, Shobha Diwakar, joining us from YouTube. Shobha is an engineering director managing the team that powers all models for ads recommendations on YouTube. Shobha's talk will be about ads recommendations and the algorithms and models used in the system. So, welcome, Shobha.
Thank you, Islam, and thanks for having me here. Hi everyone. My name is Shobha Diwakar, and I'm an engineering director at Google. I manage the YouTube Ads machine learning org. My team is responsible for building all the machine learning models used for making ad recommendations on YouTube. In my talk today, I'm going to present a very high level overview of how ad recommendations are made on YouTube. I'll focus on the products, surfaces, and will touch upon some of the machine learning areas. I would like to mention that this deck covers the work of several engineers on the team. YouTube is video for everyone. Viewers have diverse content on YouTube, whether it is staying updated with the latest news, keeping fit with at-home workouts, learning new skills, or unwinding with new entertainment from their favorite creators. Viewers can find and discover content and creators that reflect their diverse experiences and passions. We have seen people turn to YouTube more than ever, with 2 billion plus monthly logged in users watching more than a billion hours of video per day across 100 plus countries and 80 plus languages. YouTube advertising is a big business now, reaching 8.6 billion in quarterly ads revenue in Q4 of 2021. YouTube has many surfaces for content. The homepage is what you see when you first open YouTube. It displays a mixture of personalized recommendations, subscriptions, and the latest news and information. The watch page appears when you're watching a video. It suggests additional content based on whatever you're currently watching, along with videos that you may be interested in. The search page delivers relevant search results based on viewers' query. YouTube ads are the ads which show up on all these different surfaces on YouTube. There are text, image, and video ads which are interspersed with the organic content on YouTube across all these different surfaces. Deciding which ad to show in all these places requires us to predict which ad should be shown in the current context. My team builds many machine learning models across all these surfaces, formats, and objectives. All these models are used for scoring and recommending which ad to show. Next, I'll talk about the different goals of the YouTube ads recommendation system. We build models and make recommendations across all these surfaces, formats, products, and aim to deliver viewer satisfaction, advertiser value, and support the creator ecosystem. I'll discuss each of these goals in the upcoming slides. We develop models which can work well and recommend ads on all the YouTube surfaces I just talked about. The first surface is the watch page. This is a video on video recommendation problem where we are trying to show ads dependent on the organic video. We build models to predict the following: ad placement, where the ad should be shown before, during, or after the video; ad selection, which ad should be picked and shown; ad format, which ad format should be used. The ad formats available are skippable ads, where we show a skip button at 5 seconds of the ad, and the user has a choice to skip the ad; non-skippable ads, which users cannot skip but help to deliver the entire message to the users; and bumper ads, which are much shorter, 6-second ads. The next surface is YouTube feeds, like the home page and the watch page. The key aspect about feed ads are that they encourage product discovery while viewers are searching for organic content to engage with. We build models to predict the following: ad placement, the ads appear interspersed within the scrollable feed. Models decide how many and where to show the ads. Ad selection, models determine which ad needs to be shown. And formats. The formats on feed can be text or image or video ads, and they can be of different sizes and dimensions. There are different user interactions on the ad possible: clicking the ad to play the video, or even clicking on the ad directly to engage further with the ad. Finally, the last surface is the search page. This is a video or image to query recommendation problem where the query serves as a context. The model finds the best ad relevant to the search query. Search page is still a feed, and hence the ad experience is similar to other feeds. The ad placement and ad format selection are also similar to what I just described in the previous slide. The next goal is to identify the best ad formats to show. YouTube is a visually rich platform, and the ad formats are accordingly very rich and varied. There are a lot of image, text, and video formats and multiple variations on each of them. We have carousel ads, site links, and product feeds. The prediction models need to be format aware and determine the format which will work best in the current context for maximum effectiveness. Our next goal is to deliver a useful and relevant ads experience to viewers on YouTube. We have made investments in ensuring that our ads are relevant to the viewer's interests and context and use various signals for capturing relevance. An ad can be relevant to the search query, the video, or the viewer's interests. There are several ways of predicting ad relevance. Click-through rate and conversion rate models indicate the user was interested and engaged in the ad. Semantic relevance of the ad to the context also helps to deliver a more relevant ad experience. All these relevance predictors are then used for influencing scoring and ad allocation. We run a long-term value auction where we consider user satisfaction as well. We also have several viewer metrics which capture the relevance and usefulness of ads on YouTube. This helps in making our ad experience better for our viewers. Along with relevance, we want to ensure a good and safe ad experience on YouTube. What are bad experiences? The ads which are racy, offensive, clickbaity, or of just a bad quality lead to a bad experience for viewers. We have built classifiers which can classify and differentiate between these good and bad creatives and use this to ensure we maintain a bar on the quality of ads which are shown on YouTube. The next goal is to help advertisers grow their business. We have many advertisers on YouTube optimizing for different advertising goals. YouTube has both brand and performance or direct response advertising products. These span awareness, consideration, and action goals for our advertisers. We build machine learning models to predict across the entire spectrum. Brand ads are ads that are designed to capture viewers' attention and interests, optimizing for reach and views. Direct response or performance ads enable viewers to take action on the ad, optimizing for actions, sales, and purchases. On the brand side, the main purpose of a brand advertising campaign is to raise awareness and visibility of the advertiser's product, service, or cause and motivate audiences to engage with the advertiser's brand and its associated products. For advertisers optimizing for efficient reach on YouTube, we do a multi-format optimization across different formats like short ads or bumpers or skippable in-stream ads. Advertisers can also choose to use non-skippable ads, which helps to deliver brand awareness on the entire message. YouTube also has a masthead which is suitable for advertisers who want to display their ad in a prominent space on the YouTube home feed. Another interesting aspect in the optimization space is that all these types of advertising objectives are not just supported via an ads auction, but also via reservation, where advertisers can buy impressions at a fixed rate. All these different objectives and products makes our marketplace optimization quite complex and interesting. Performance advertising optimizes for advertiser conversions and value in real time using automated bidding solutions. The ad provides a call to action button which can install an app or subscribe to a service so that viewers can take action on the ad. We support many different types of advertiser conversions and products optimizing for them. We build again optimization and custom learning solutions for them, which I'll describe in the slides next. The first product is app campaigns. App campaigns are used by app advertisers to promote and increase engagement with their app. We optimize for different goals: app installs, in-app actions on the app, and value. To match ads to their viewers, we have models which understand the intent and the purpose of the app and the action and the viewer's interests. This allows us to find the best viewers for the advertiser's app. The next product is video action campaigns, and this is used by advertisers to drive up website traffic, leads, and sales. Advertisers can customize the ad by adding prominent calls to action, headline text overlays, end screens, site links, lead forms to drive up their conversions as well. We build models to optimize across all these heterogeneous conversion types and formats. The next is discovery campaigns, and these are specially designed for feed surfaces and optimized to drive up website traffic, leads, and sales for advertisers. They also provide an ability for advertisers to showcase their products in a multi-image carousel format. Moving on, I would like to also say that a very important goal of our system is to support a diverse ecosystem of creators and give over 2 billion viewers globally access to YouTube content for free. I am next going to talk about the YouTube ads machine learning landscape. The team works on multiple areas, and I'm going to briefly talk about them at a very high level today. I won't be going into the very specific algorithmic details in the talk. First, I'll talk about the end-to-end recommendations lifecycle. When the user opens a video, an ad request is sent to our system. Note the organic and ad recommendation stacks are completely different and independent from each other. The ad's recommendation is redirected to an ad server, which processes the request. The first step is to pick all the eligible ads from our ads inventory. We then have a retrieval stack, which picks the top key ads, which are most likely to win. The retrieval flow on YouTube is predominantly queryless. We also use a single, unified retrieval system across all the surfaces and demand types, which brings in additional challenges in the design of the system. We then score all these ads, and the score is generated by a combination of many different types of models. The models predict click-through rates, conversion rates, ad relevance, etc. These are then combined to form a score, which is then used for ad selection. These are deep models, and we use TensorFlow to build our models. These models use online training and are trained continuously. Every few hours, we do push out model versions to serving, since models need to be fresh and make accurate predictions and to capture the dynamic environment. The model predictions are then used to generate a score, which is used for ad ranking, where the ad is selected by running an ads auction. The winning ad or ads for multi-slot cases are then rendered on the YouTube page. The response to the ads, clicks on the ads, or conversions are then fed back to the model for training. There are multiple pillars for model development we focus on. The first one is development of new models. The YouTube ads landscape is quite dynamic, and we keep on releasing new products and ad experiences. This necessitates developing new models from scratch. First, we identify bootstrap training data. We typically pick an existing dataset which is similar in distributions for the optimization problem at hand. Then we identify the right objective the model needs to optimize and the feature set and design the model. We use several machine learning techniques which help with cold start that arises due to the model having limited data during the ramp up phase. We then build and iterate based on viewer and advertiser feedback and take it to launch. The second pillar is feature engineering. We invest a lot in identifying, designing new query, viewer, video, and ad features. These features may be sparse or dense, and we use representation learning algorithms to generate embeddings and clusters. The third pillar is designing custom loss functions and model architectures. We may apply different state of the art machine learning techniques to improve model performance, work on model design, and hyperparameters to improve performance. The last pillar is evaluation and experimentation. We have a suite of offline metrics which capture model performance. We capture this on multiple slices. We then experiment on live traffic and look at user happiness and advertiser value metrics as well. Next, I'm going to talk about retrieval and scoring. We have a huge ad inventory comprising of a lot of ads and advertiser assets. We need to pick one best ad amongst all of them. Our scoring models are deep models, which are quite huge with lots of features. These are expensive compute and latency wise. Hence, it's not very optimal to score each and every candidate. We use lightweight two-tower models for making predictions during the retrieval stage. We use a unified retrieval model design, which is able to work well across diverse products and surfaces. The query here can be the search query or the video or other context. Next, I'll talk about the deep model architectures. We do invest a lot in designing and developing new architectures for our models. We use several sophisticated model architectures and keep on evolving them over time. We have made investments in using state-of-the-art techniques for improving model performance. Example, sequence models, attention, BERT, and other computer vision algorithms. Transfer learning is also a technique we use to learn across different click and conversion objectives. We also rely on multitask learning to learn across different prediction tasks. Next, I'll cover content understanding. So YouTube is rich with multiple modalities like text, image, audio, video, as shown on the slide. Video creatives use video, audio, text for effective storytelling, and we need to be able to understand the message the creators are trying to convey. For example, just looking at the visual elements on the ad does not really capture the emotion the ad is trying to convey via audio. Therefore, we need to look at all these different modalities of the ads. We need to develop different sophisticated algorithms to capture all these nuances. The recommendation models need to be able to work well across these modalities to make good recommendations. We use a variety of supervised and self-supervised learning algorithms and state-of-the-art NLP and vision multimodal techniques to learn embedding and clusters of ad content. This allows us to develop sparse and dense representations of the creators, which are then used across our models. Next, I'll talk about viewer interests. We seek to understand the aggregated and anonymous viewer interests on YouTube to be able to show relevant ads to them. We use aggregated and anonymous insights on YouTube such as the videos they watch, the channels they engage in, and the topics they are interested in. We use several feed-forward models using supervised learning, sequence models, and clustering techniques to learn interests and topics of viewers. Scalability is the next area I am going to talk about. The deep models handle billions of examples, and we serve high volumes of traffic with strict latency and resource constraints. We need to work on developing resource efficient models, especially as the size and scale of the models keeps on growing with time. For this, we train and serve on tensor processing unit, accelerated hardware, which allows us to train larger complex neural network models efficiently. We also develop resource efficient model architectures, which are specifically designed to optimize for storage and compute of large scale models. We rely on techniques like distillation to build larger models and serve smaller versions of them, thereby making it tractable to utilize more expansive set of complex architectures. Next, I'll cover reliability. So YouTube Ads is a large-scale recommendation systems serving billions of queries with strict latency constraints, which requires us to have a scalable but also robust and reliable infrastructure. We need our model training and serving infrastructures to be able to reliably train and serve models in real time. We also want to have a scalable feature stack and feature generation and processing capabilities for enhancing all these models. All these models are serving live traffic, and therefore, we also spend a lot of effort on productionizing these models well with proper monitoring and alerting. This is especially important to ensure model correctness and freshness, as they have a large impact on model performance and hence online serving metrics as well. This is the end of my talk. So thank you everyone for attending the talk. And just wanted to say that my team is hiring across all levels. So please do reach out to me. If you're either interested in learning more about the area, you can directly reach me on LinkedIn as well. Thank you.
Thank you so much, Shobha, for that talk. That was very interesting and insightful. So we have time for only a few questions. So let me get started. So the first one says, like, given the large number of optimization functions that you deal with, how do you prevent explosion in the number of models?
That's a great question. So, I mean, fundamentally, we want to have and restrict the number of models we have, like the amount of surfaces and prediction goals we have. You can really end up having a big explosion in that space. So what we do that is we actually try to make sure we restrict the number of models. This mainly allows for simplicity because it's much easier to think about, it's much easier to iterate on it. It also allows us to have faster velocity when we are just doing some of these improvements across all the models. But that being said, at times the distributions are also very different and the objectives are different. So we do decide to have a different model as well. We also rely a lot on transfer learning and multitask learning to learn across these relative objectives so that we can make this good trade-off between flexibility, velocity of model development, and simplicity. So we do a lot of effort on balancing these things out by like a lot of transfer learning and sharing across different model types and spaces.
Got it. So the next question is, so do you do value prediction? And if yes, like, what are some of the challenges and the use cases that you do with it?
So yes, we do support return on advertising spend for advertisers. We have products which actually optimize for that. For example, for app campaigns, we do have an option where advertisers can actually specify values on different conversion types so that we can actually get the value of those of the advertiser and of the specific ad. And for campaigns focused on achieving a return on advertising spend, they do set a target return on advertising spend as a percentage value per spend. And then we actually use this to optimize. I would say the main challenges are, one is sparsity. Like this problem deals with a lot more sparsity, so we have to apply different techniques for that. The other one is we also have to have and redefine our loss functions to make them more custom to handle this, because there's a lot of heterogeneity in the scale of the values and even the type of advertisers or the type of things we're actually dealing with, and which is why this problem is a lot more tricky. But we do have like a lot more custom techniques we apply, for example, which is different from a regular conversion based optimization as well.
I see. All right. Thanks again, Shobha, for the talk and for answering the questions. Now we're going to move on to our next talk. So I'd like to welcome and introduce Joshua Cherry. Josh is an engineer and an economist on the ads marketplace team at Pinterest. He works on market design, allocation and pricing, experimental methods, and causal inference. He will talk about some of the challenges and opportunities in marketplace design. So welcome, Josh.
Thank you, Islam, and thank you everyone for attending. Very glad to be here. So I'm going to be talking about the challenges and opportunities in marketplace design. And before I get into that, I think it'd be worth discussing what is marketplace design? What does it mean to design a marketplace? Paul Milgrom, a recent Nobel laureate, in his numbers lecture many years ago, offered this definition of market design. So the market design is a kind of economic engineering that utilizes laboratory research, game theory, algorithms, simulations, and more. Its challenges inspire us to rethink long-standing fundamentals of economic theory. The distinction that he's making is that in the past, economists mostly studied markets that existed, and this is in creating the rules for interactions ahead of time. And how might you do that if you could set those rules? In industry, particularly here at Pinterest, I would amend this definition a little bit. I'd say the marketplace design is a kind of economic engineering, utilizing economic theory, game theory, but also software development, experimentation, machine learning, and more. And its challenges inspire us to rethink product, science, and engineering choices, and to think about contributing to industry standards and the aspects of particular implementations. Okay, so there's kind of a connection between product and marketplace design in that you need to think about what it is that you're going to offer to sell and structure and allow to participate. And that goes hand in hand with the details of how you would implement systems to achieve those goals. Ad markets are often characterized by selling ads by auctions. So why do we run auctions? This is true not just in ad auctions, or in the ad context, but more generally, we run auctions to elicit information from bidders. And the reason why you'd like to elicit this information is so that you can find out who values what and decide best who to give things to. Okay? So you need to figure out which ads are to be shown and how much to charge, and finding out from bidders how much things are worth allows you to do that efficiently. Okay? Efficiency here means allocative efficiency, so the size of the pie. You're trying to maximize the match value between ads and users, with some fraction of that being kept to the platform as revenue. So how have ads marketplaces evolved in the, say, 20, 25 years that they've existed? In the past, there were just a traditional auction where advertisers would place a bid. And the bid was supposed to reflect their willingness to pay per impression or click or some other billable event. But recent innovations have moved ad marketplaces towards automation. So many ad platforms offer ad products that have a lot of automation. This automation can target a particular amount of spend, so try to maximize the number of events, like impressions or clicks, available for a given amount of budget, or to target a certain performance. Spend as much as you can, subject to performance not being worse than some threshold. The punchline being that lots of things are automated that didn't used to be. And this imposes new challenges on market design. You need to think about how to construct a bid on behalf of an advertiser and how to interpret the bids that you, the marketplace designer, have constructed. You need to think about feedback effects from controllers that are actually implementing the automation that ad marketplaces offer on behalf of advertisers. The consequence of all this is that there are a lot of feedbacks and equilibrium effects that need to be accounted for. And when these things are present, it can confound certain measurement techniques that people have kind of historically taken for granted, say through experimentation or data analysis. Okay. And in this talk, I'm going to try to touch on two classes of causal inference problems that come up in marketplaces and marketplace design. One of which is experimentation in a world where there's a lot of automation, and the other being issues related to LTV, long-term value, the future consequences of interventions that a marketplace can have on its users. Okay, so what does a marketplace look like when you're trying to do experiments? Historically, platform experimentation systems were set up to do user randomized experiments, and they're really great for learning user effects in this way. You want to learn if a particular font or color or placement of a button is better for users. This is an excellent way to do this. In a marketplace, the economic forces kind of put extra demands on what it means to separate treatment and control. Okay, so things like budget constraints, bid automation, and other automation techniques used by advertisers in a multi-sided market necessarily cause spillovers between groups in your experiments. So what I'm going to try to do is walk through the simplest possible example of this I can come up with to highlight what goes wrong with a naive application of A/B testing in a marketplace. Okay, so right now you have your control situation running in production. And if you were to launch an alternative experience, you'd have this red bar. This is the outcome of some treated state. And if there are no spillovers between treatment and control, you could divide your population of users in half and do an A/B test. And one half of it would look like control and one half of it would look like treatment. In a marketplace context, this doesn't happen, and you get bleeding between the two. The bleeding comes from the coupling through things like budgets and automated bidding that make it so that users are coupled to advertisers, and advertisers face all users and not just a subset of users. So, and this is something that's not even unique to ad marketplaces. You can imagine that this is the case, say it's something like Uber with drivers and riders. Becomes difficult to do experimentation just on drivers, for example, or it's something like a social network where there are connections between users that need to be accounted for. Okay, so here, let's imagine that we want to do an experiment with the ad load on a particular platform. So what is the available supply that we have? Well, there's some overall amount of organic supply. This is the organic content on the platform. Say on Pinterest, these are the pins. And just for simplicity, I'm going to make a lot of assumptions. Okay, this is fixed and it's uniformly distributed throughout the day. Okay, and the ad supply is directly controlled by something that we'll call ad load, which is the proportion of the total amount of content that is ads. Okay, to make the math of the arithmetic easy, let's just say that there's 100 total impression opportunities available to begin with. Okay. What's going on with the demand side? Okay. Well, let's just again simplify greatly and suppose that all advertising budget is represented by an auto bidder. And this auto bidder aims to fulfill budget in full. Okay, so it will bid up and down according to the available supply to try to exhaust the budget in a day. Okay. Now let's just assume that this does this perfectly and uniformly through time. Okay. Again, to make the arithmetic easy, let's suppose that there's $100 of budgets in total. Okay. So what happens in production right now? Well, we know that there's $100 of spend on 100 impressions, so we're expecting a CPM of $1. Okay. And now we ask the question, what would happen if we were to increase the ad load by 20%? Well, I shouldn't shock anyone to know that you'd spend $100 on 120 impressions and your CPM would fall to 83 cents. But what would an A/B test tell us in this context? So what if we did this in an experiment? Okay. So the classic setting, user randomized, this is what we would get. Okay. The control arm has half of the, the original 50 impression opportunities. That's half of the 100. And in the treatment group, we're trying to give 20% higher. So there's 60 over there. Okay. So again, we have $100 of total budget that's now going to be exhausted over 110 impressions available in the marketplace. Now this should, in aggregate, yield a cost per impression of 91 cents. Okay. So you might expect in your experimentation platform a results table that looks kind of like this. You'd see a lift of impressions of 20%, no change in prices between treatment and control, and a 20% increase in revenue. This is a little problematic because we started with the assumption that there's $100 of budget. How can we be introducing an intervention that's expected to increase revenue by 20%? A common thing that's used in industry, Pinterest and elsewhere, is a technique called budget segmentation. I've also heard the terms virtual budgets and some other terms, state. And essentially what this does is it makes it so that groups in your experiment are limited to their proportion of the total available budget. Okay, so what might this kind of test look like? Control is again given 50 impression opportunities and will limit spend on that group to $50, which is half. The treatment group is given 60 impression opportunities, 20% higher, and they're also limited to spending $50 in that group. Okay. The big controller, again, will see $100 of budget trying to be spent on 110 impressions in the marketplace. So as before, we have a cost per impression, 91 cents. But this is true until one of these groups hits their budget cap. In this example, this happens at hour 22. So if in the treatment group, you spend at 91 cents, you'll end up delivering 55 impressions, not 60. The controller, looking at the marketplace as a whole, sees unspent budget and cranks up bids to ensure that the budget market-wide is delivered in full. And for the last bit of the day, the prices are actually much higher. Also, at the end of the day, spend is only occurring in the control group. So your experiment might report results like this. Okay. Control sees 50 impressions, spends $50 in total, yields a cost per impression of $1. Treatment group sees 55 impressions, a CPM of 91 cents. They spend the budget in full. Okay, so now we have no change in revenue, a 10% decrease in cost per impression, and a 10% increase in ad load. This seems also problematic because by construction, this experiment should be inducing a 20% increase in ad load, not a 10% increase in ad load. A solution for this, an experimental solution for this, would be to segment bids as well. So this is an experimental design where, in addition to constraining the spend in each group, you also endow each of the groups with their own bid controller. Okay? So again, the control group is given 50 impression opportunities, its own bid controller, and is allowed to spend up to $50. The treatment group is given 60 impression opportunities, its own bid controller, and is allowed to spend up to $50. The control group will bid to exhaust its budget on its available impressions for a cost per impression of $1. The treatment group will bid so that it exhausts its budget on the 60 available impressions for a cost per impression of 83 cents. And now we have no change in revenue and the 17% decrease in CPM that we were expecting. And now Gumby can be happy. So what should you take away from this? Marketplace dynamics can cause spillovers between treatment and control groups, and this can cause problems in making inference from experiments. So in a marketplace setting, it is not the case that just running an A/B test naively necessarily gives you the measurement of the treatment effects that you're interested in. These controllers that automate behaviors on behalf of advertisers do so by doing things like manipulating bids. Okay. So how do we interpret these bids that are coming out of these controllers? Right? This is in contrast to years past when advertisers would show up and say, this is my bid, this is how much something is actually worth to me. In this example, we saw a price path that actually fluctuated, a bid path that fluctuated, even though there was nothing that we did that necessarily suggested that an advertiser actually had a different valuation for what they were winning. Right? So how well is an auto bidder revealing an advertiser willingness to pay? What is willingness to pay when auto bids represent the advertiser's intent? Okay. So these are things to think about when you're designing experiments and also when you're analyzing experimental results. This then leads into kind of a broader set of questions related to long-term value. So suppose now you've sorted out some of the stuff with the experimentation. You've now induced a change, like say increasing ad load, and you know that it has some effects on revenue and some effects on advertiser performance. So how would you use this information to make decisions? How would you actually evaluate whether or not it was a good idea to make that change? To do that, following this example, you'd want to know how ad load today affects users tomorrow. And the reason why you want to do this is to the extent that ad load affects users negatively, it affects their future engagement and the future ad supply you have available. This affects your monetization opportunities and your future ability to satisfy advertisers' goals. Okay. Now you might imagine that in principle, there would be some policy that you could do, say for ad load, that optimizes the long run revenue. How could you find that? How could you pose this question? Right? What you need to do is figure out how to measure or infer or reason about the future consequences on engagement for interventions that you make today to changing the rules of the marketplace right now. So what is LTV and what isn't LTV? To a lot of people in a lot of contexts, LTV sounds like a forecast. You're talking about what will this user do in the future? How much future engagement might we see from this user? How likely we are to retain this user? But a forecast is not the right approach for choosing a policy. You want to know what would happen if you intervened. Right? You want to know how this forecast would be different under different market conditions. Right? Okay, and this is kind of the fundamental difference between prediction and causal inference. So to use something for making policy, for intervening and expecting that your interventions are properly accounted for in a long-term sense, you want something that has a causal interpretation. Well, why is this difficult? Well, it's difficult for a number of reasons. As I mentioned before, standard statistical tools related to forecasting are just not suited for evaluating interventions. You're going out of sample, or your forecast is not properly reflecting the causal relationships that govern your environment. And maybe you should just do long-term experiments. Well, that might work sometimes, but maintaining long-term experiments can be expensive. Certain long-term experiments can be infeasible, too disruptive to users, and so on. A common approach in industry is to use something called surrogates. And this is to construct a set of kind of proxy experimental endpoints that can be observed in a short run. And you look for your effects of interventions on your set of surrogates, or these surrogate endpoints, and combine that with a separate notion of how these surrogates relate to the long-term objects of interest. Sometimes these surrogate approaches can be a bit difficult to interpret, and it's not always clear that you can validate that your set of surrogates is sufficient. So here, we'll describe a different approach to representing long-term value from users that I'll argue sidesteps some of these concerns. Okay. So suppose you posited that a user has behavior that's described by transitions between states. So the states can be things like, are they active or inactive? What sorts of activities they're engaging in at the time? Characteristics of the experience that they've had in the recent past. Good examples of this on Pinterest might be whether searching or browsing, consuming content, or creating content. These will be somewhat domain specific. You use experiments to get a good causal estimate of what your intervention does to these transition probabilities. So again, you've assumed that behavior is governed by these processes, and your interventions modify the processes by which users transit between these states. And that, combined with the use of the Markovian structure, can deliver causal estimates of long-term effects from short-run experiments. Some other nice things about this kind of approach: it's a bit more interpretable than some more black box things like surrogates. It's a little bit easier to validate the assumptions of the model. For example, you could test whether your Markovian assumptions are satisfied. You have visibility into the path that's being taken by users over some horizon of your choice, not just the sum over, say, the 6 months or year that you would set up to evaluate long-term effects. So what might this actually look like? We'll describe user states by something like this. This is the state of users at time t. And we're imagining that this is kind of grabbing the information between some beginning and now. We'll have some reward function that describes how good it is for the platform to have a user in that state at that time. The marketplace intervenes in the user experience, in this example, say by changing ad load. And then this changes the transition process. Now you can imagine playing that forward and saying, well, what would be the stationary distribution of over states, users following this other process? Okay, so this might be some example of a unidimensional state. You have some activity on some days, no activity on others. The intensity of the activity varies over time, right? And you're accumulating these sorts of paths across all of the users, and you're trying to estimate these transition probabilities. How can you use such a model to actually evaluate the marketplace interventions? So how would you use this to answer questions like, what is the impact of an increase in ad load on the distribution of these user paths? These are paths through state space, right? So you would have this model as I described before, but now you're in an experimental setting, and you could estimate this on your treatment group as well. Okay, so then how does this translate experimental outcomes into long-term value? Well, what you'll do is you'll observe the state transitions during the horizon of your experiment to get separate estimates of this transition process for each of your experimental groups. You do this with your favorite technique, but a suggestion would be something non-parametric. It would basically be kind of a frequency estimator of the rate of transition between these states for users in these groups. And that gives estimators with good properties. And as I alluded to before, you use these estimated transition matrices to project forward the distribution of aggregate behavior in each of these groups. So typical path for control might be something like the blue line, and typical transition paths for someone in treatment might be like the red line. Okay? And you're aggregating over all the users in the experimental groups. So to conclude, to optimize a marketplace, you need to account for both short and long-term effects, and you need to account for equilibrium effects, even in the short run. You're dealing with a multi-sided market and competition between participants in these markets. And these participants are increasingly using automation that further couples their behavior across large portions of the environment. Okay. And because these marketplaces are presenting unique challenges, you need clever techniques, experimental, econometric, and so on, to get good estimates of what your interventions will do. Short-run experiments, as I mentioned, can be leveraged to get causal estimates of long-term effects. This is coming from imposing some structure and some domain knowledge on how you believe the users respond to these things. So with that, I will conclude and leave time for questions. And I wanted to thank some people who have worked on our implementations of these sorts of things at Pinterest. So Andre, Dan, and Alex, who are no longer here. Joachim, Yang, Philip, Akanksha, and Raghavan. So with that, I'm happy to take questions.
Hi, everyone. My name is Sindhu Raghavan, and I lead the ads ranking organization at Pinterest. I'll be your moderator for the rest of the session. I'd first like to thank Josh for the very interesting and insightful presentation on marketplace design, where he described all the challenges and opportunities that we have in this area. Josh, we have a number of questions coming in from the audience. They're eager to have their questions answered. I would like to move on to Q&A with Josh on this topic. First question, Josh. How do you combine different signals going into marketplace? I would imagine, we have, we predict engagement, relevance, and, a whole lot of other signals that go into marketplace. How do you combine these, and what do you optimize for when you're combining them?
So I'll go into the exact details of what we do in the Pinterest auction, but more generally, an ad platform is a for-profit business and is trying to maximize the long-term profit of its company, and so it's trying to make choices at every moment that are consistent with that. So you could sort of imagine the thought experiment of what would you do if you could pause the universe and think about all of the long-term effects from showing any combination of ads that you have available in your candidate set at that moment. And moreover, what would be all these long-term effects if you were to price these ads in one way or another? This thought process would lead you to things like, it's not just advertiser bids that are important in the ranking, but other user characteristics. I know Shobha used the term long-term auction. I imagine that that's very similar to things that are common in the industry, where you're kind of combining something that represents the value to an advertising partner and value to your users coming from the different characteristics of the ads affecting the experience. So you will be trying to rank ads in an auction by something that combines the concerns for making money. This would be primarily through the advertiser bid part of it, and user retention and satisfaction and future opportunities to sell ads, and that's coming from things that represent user concerns.
Thank you. Moving on to next question. Are there other sources of spillover interference in marketplace?
Yes, there are many. A lot of them you and others are probably familiar with. Often models are trained on all data, and that data comes from both treatment and control groups of experiments. These are probably ignorable types of spillovers in most circumstances, but theoretically they're still there. Anything that couples the behavior between the two groups is a source of spillover. And the exercises in determining which ones are really first order, which ones are going to influence your results so much that you might draw the wrong conclusions and make the wrong decisions.
Okay, thank you. Moving on, what are your thoughts on switchback experiments to try to account for spillover and network effects?
Switchback, I'm guessing, refers to turning on and off, for having a holdback at the end of your experimental run. So those are good, I think, for evaluating whether or not the experimental results are spurious or real. But that doesn't directly affect your assessment of spillovers, which comes from the coupling. And so the switchback or holdout type approach still suffers from the problems of both of your experimental groups being coupled through the behavior of the participants on the other side of the market. So you're still doing a user randomized experiment, and you're still exposing all of those the users in both of those groups to all advertisers, all algorithmic feedback of those advertisers, budget constraints of those advertisers, so forth. So these are good things to have in your toolkit, but they're not going to by themselves fix a lot of these problems.
Moving on to your next question, can all equilibrium effects be captured experimentally?
That's a tricky one. In principle, yes. In practice, I would say no. So to truly capture all equilibrium effects experimentally, you really need to be separating everything into all of their own universes. So this is really like kind of a true splitting of the future evolution of the universe, not just your marketplace. To the extent that you can identify equilibrium effects of interest, you can design experiments that capture, at least to first order, the problems of the spillovers for that type of thing. Like as I alluded to with the spillovers coming from, say, a shared bid controller that is experimentally handled by endowing each experiment group with its own bid controller.
Okay, moving on. This is a slightly different question. What are methodologies you use to understand advertiser evaluation in automated bidding world?
I'm not entirely sure I understand the question. Let me see if I can answer what I think the question might have been. So I'll infer that this means, what are you doing to assign what we believe to be the advertiser's value in a situation when the advertiser didn't tell us what the value was? And in that case, largely what you're doing is you're looking at temporal feedback from the advertiser. You can gain inference about the advertiser's preferences by looking at campaign setting changes that they make over time. Whenever you observe that they make a decision, they change their budgets, they changed their creatives, they changed something else about their campaigns, you can infer that they like what they have now more than what they had previously. And repeated application of this logic builds a set of inequality constraints on what the advertiser might believe and what the advertiser actually values. And this can sometimes be used to get interval estimates for advertiser values just from the observational data of their responses to realized performances.
Thank you for that. And the next couple of questions are on the topic of LTV and markup processes. So here's one. Did you evaluate the LTV for markup process versus the surrogate approaches?
We don't have a full surrogate implementation, so we couldn't put this head to head. A full surrogate approach relies on the surrogacy assumption, which is that the set of surrogates mediates all causal paths between your intervention and your endpoint. It's very challenging to build a really robust surrogate approach. I've seen it elsewhere, and it can work very well. But we didn't put them head to head.
Okay. Last question, and somewhat related to the previous question. Have you tried to evaluate, backtest the performance of the Markov model LTV value against realized data?
Yes, and it fits well. I don't have any slides on the goodness of fit evaluation to share, unfortunately, but it does work quite well.
Thank you once again, Josh, for the talk and for answering all these questions. Welcome back, everyone. For our last talk, I would like to invite Joey Robinson from Snapchat, who will talk about knowledge distillation for ranking and recommendations. Joey is a machine learning engineer in Snapchat's ads ranking machine learning modeling team, where he focuses on model architecture and training processes for app event CVR models. Over to you, Joey.
Great. Well, hi, everyone, and thanks for joining today. I'm going to go ahead and skip to the next slide to introduce myself, and then we can get into some of the actual content. So yeah, my name is Joey Robinson. I work at Snapchat on the modeling team within ad ranking, where I've been for the past 2.5 years or so. At Snap, we're one of the primary teams responsible for developing the machine learning models that are used to predict conversion events, such as an app install or a purchase, as part of the ad personalization system. And we work in close collaboration with feature engineering and product teams. Similar to other advertising platforms, Snap allows advertisers to bid on conversion events that they care about, things like visiting a website, installing an app, or perhaps making a purchase. And for each of these conversion events, for each important action that a user could take, there is, give me 1 second, I'm gonna switch the audio out. There we go. Let's try this again. So as I was saying, similar to other advertising platforms, Snap allows advertisers to bid on conversion events that they care about. So I said things like installing an app, visiting a website, or perhaps making a purchase. And then for each of these conversion events, there is some ML model that's responsible for predicting whether the user will take that action after seeing an ad. In terms of content, let's start by talking about the ad auction process a bit. When a user visits the Snapchat app and there's an opportunity to show an ad, we need to decide which particular ad do we show among all possible ads. The ad auction, it's the component that's responsible for matching the Snapchat user with a personalized ad out of the millions of possible ads in our ad inventory. And in practice, the auction works roughly as follows. We first take all of the possible ads and we see which ads are even applicable to the user. So some ads might, for instance, have a constraint that they're only shown to males in California. So if the user isn't that, we can ignore the ad. Some ads might not have any budget left to spend. So again, we don't show that ad, and so on for various other ad eligibility checks. From there, we have a set of lightweight machine learning models that score each of the ads and filter the total set of applicable ads down to what's known as the auction participants. These lightweight models, they don't have to be the most accurate. They just need to reliably let through the best set of ads to be scored by the next stage. And in terms of scale, there's generally around 1,000 or so auction participants, plus or minus, that come out of this stage. Now, finally, we take the heavy ML models and we score each of the auction participants, predicting things like probability of installing an app, probability of a click, and so on. Those scores are sent directly to the ad auction. The auction picks the winning ad using a combination of model scores and other information, and we show that ad to the user. So now the user has seen the ad and we want to know, did they like it, or how did they respond? We capture this through the user's in-app actions, such as whether they clicked on the ad, as well as off-app actions, like whether they installed the app from the ad or purchased the item in the ad. And we use that feedback as labels to update our ML models. Those labels are then joined with serving time features of the displayed ad in order to construct training data for the heavy ranking models. So just to briefly recap, each row of the heavy model training data consists of one ad impression, one ad that was shown to the user. We have features for the ad, the user that we showed the ad to, as well as the current context. And then as labels, we have the action that the user took after seeing the ad. So did they click on it? How long did they view it? Did they purchase the item, etc.? All right, so what does all this mean for the heavy ranking models? First, we see that these models only train on the auction winners. These are the only ads that we actually showed to the user, so they're the only ads for which we actually have training labels. However, the model has to make predictions on all of the auction participants that are passed to it from earlier stages, and so you can see there's a clear mismatch here. The model only gets to train on what are presumably some of the best, most relevant ads. But then when you start serving predictions with that model, all of a sudden it is expected to make predictions on a variety of bad or poorly matched ads that it's never seen before. This gets me to my second awkward point, which is that this mismatch between training and serving data distributions, it favors the current production model. So your production model, it actually has the opportunity to influence the collection of future training data. When that prod model overpredicts the relevance of an ad, and that ad gets shown to the user's negative feedback or their lack of engagement, that then ends up in the training data to allow the production model to correct itself. So the current production model, it has this really high quality feedback loop that better allows it to learn from and to correct its own overpredictions. On the other hand, any new model that you train on auction winners, it's going to be working in a purely observational setting. So it sees the ads that the production model chose, but it has no awareness of the other ads that it will need to score once it's put online. It has no awareness of the auction participants. You can see the implications of this selection bias in these two figures. So I've taken a sample of the auction participants, and I've scored that data with both a current production model and a retrained version of that production model, where the model was trained on a newer data set. On the left, I plotted a histogram of the terms for symmetric mean absolute percent error between the retrained prod model's predictions and the actual prod model. And I've plotted these without the absolute value component so that we can distinguish between overpredictions and underpredictions. SMAPE, for those of you who aren't familiar, it's a measure of how much two predictions differ. You calculate the difference between the scores, divide by the average of scores, and you convert that to a percentage. And then you just average that across all your training examples. So in that histogram on the left, a value of 50, that means that the retrained model score is 50% higher than the average score of it and the production model. And a value of minus 100 means that the retrained model score is 100% lower than the average score of it and the prod model. I also summarize this information on the right-hand table where we can, where here we report each model's average prediction score relative to the prod model's prediction on auction winners. And what you can see is that on average, the retrained model scores, they're substantially higher on auction participants, around 3x higher on average compared to the prod model. This is despite the fact that per our offline metrics, both of these models produce the same average score on auction winners. So what we're seeing here, it's a direct result of the selection bias in the training data and a mismatch in the data distribution between auction participants and auction winners. On average, the prod model, it gives auction participants an 8 times lower score compared to auction winners. But the retrained prod model, it only gives auction participants a 2.5 times lower score than the auction winners. This causes a lot of practical problems. So for one, it makes it difficult to launch new models because the prod model, it has an unfair advantage that's very difficult to replicate offline. That prod model, it has learned things that it seems like our new models will not learn just from looking at the existing training data. And then the second issue is that it causes calibration issues for new models whenever we put them online. Because what we can see on that right-hand table is that compared to the production model, our retrained model is biased towards giving significantly higher scores on the non-winning auction participants. Again, about 3 times higher average score on the auction participants compared to our original prod model. The solution that we came up with to manage this problem is to train a model in 2 stages. So first, pre-training phase. We distill from the prod model to our new model architecture in order to train our model to produce the same score as the prod model on each auction participant. And since we're using distillation here, we don't actually need labels on this data. We're just trying to get our new model to mimic the scoring behavior of the actual prod model. Once we've achieved a reasonable level of convergence, we train the model normally on auction winners. And here we rely on the new model's improved architecture and new features in order to allow it to exceed the performance of the prod model. So first, match the behavior of the prod model, and then train on the auction winners in order to exceed the performance of the prod model. In practice, there are a couple different strategies for pre-training and training configurations that we found to work fairly well. One, you could first pre-train with the distillation loss on auction participants, then train the model normally on the labeled training data. Or to bridge the gap between auction participants and winners, you can do this in 3 stages, as I've shown in the diagram on this slide. So you can first pre-train on auction participants in order to get the new model to match the prod model scores. Then second, you can train on a mix of auction participants and winners using a distillation loss for the auction participants and a hard label loss for the auction winners. This allows the model to begin adapting to the labeled auction winner data while still encouraging the model to behave similarly to the prod model on auction participants. And then finally, in either case, we train on the auction winners in order to finish the training process. On the last slide, I mentioned that we use knowledge distillation to get our new model to match the scores of the existing prod model. Knowledge distillation, this is a technique that was introduced around 2015 with the original intent being to take an ensemble or other computationally expensive teacher model and create a smaller model called the student that is able to approximately mimic the behavior of the teacher despite its smaller size. So it was a cost and latency saving technique. You first train an accurate, very expensive model, and then you attempt to train a more lightweight variant of it that behaves similarly. Typically, this is done by having the teacher model make predictions on a large amount of data, and then you train the student using a loss between the student's predictions and the teacher's predictions. The standard loss for this is cross entropy, in which case you're effectively treating the teacher's predictions as soft probabilistic labels. And so you take some data, you pass it into both the teacher and student models, and you use the cross entropy loss in order to encourage the student's scores to match the reference scores from the teacher. Now, as I mentioned a couple slides ago, in our case, we're using knowledge distillation to align our new model with the current prod model. We take the prod model and we distill from that prod model to the new model on the auction participants as a pre-training stage, such that after this pre-training, our new model produces approximately the same scores on auction participants as the prod model. When we do this, you can see a pretty clear shift in model behavior on auction participants. So rather than systematically over-predicting on participants, the new model's predictions are now centered around the same values as the prod model's predictions. In the middle histogram, I've shown the retrained model SMAPE with respect to the original prod model just after that pre-training phase. And the average percent difference in scores between the retrained model and the prod model, that's now reduced from over 100% to around 13% or so. So with this pre-training phase, we've achieved a reasonably close match between the two model scores. And then if you look at the table on the right, you can see that the model's average participant scores are also now aligned. Both models, they're still calibrated on auction winners. They both produce the same average winner score. And both models also now give an average prediction for auction participants that's around 1/8 that of auction winners. Now that our new model produces approximately the same scores as the prod model on auction participants, we can now train it on the labeled data and make use of its improved architecture and feature set in order to exceed the performance of the prod model. Now, a couple questions that you might have are, one, how does the learned behavior on auction participants translate to auction winners? And does the behavior on auction participants hold as we incrementally update our model on new auction winner data? For the first question, we do see that the distillation process not only affects the model scores on auction participants, but that it also improves the model's performance with respect to our standard metrics on auction winners like AUC or log loss. And then for the second, yes, we do observe that the behavior on auction participants holds at least at the 1 month mark. The model's average score on auction participants after 1 month, it's still similar to that of the production model. And the percent difference in scores between it and the production model, it's still significantly reduced, around 3x lower compared to a model that doesn't use pre-training. To wrap things up on this one, this is a technique that we have successfully applied to snap ad ranking models. And it was one of several techniques that helped us to launch a model that it was a CVR model that we'd struggled to update for quite some time. And besides the ability to help us launch models, this technique can also improve cost efficiency. So rather than having to train a model on many, many months of data, you can instead train a model on a smaller amount of recent data and use the distillation pre-training to, in a way, catch the model up on the relevant information that it's missed in the preceding months. All right. I want to switch to the next topic now, which is born-again networks for ads recommendation. Typically in knowledge distillation, the teacher is more knowledgeable than the student. The teacher, it might be a large model that's impractical to serve. It could be an ensemble of many models. It could have some privileged non-servable features, but in any case, it is usually better in some sense. And you're trying to transfer the knowledge of that better model into a smaller, more lightweight model. Born-again networks, they take a slightly different approach. The idea of born-again networks, it comes from a 2018 paper in which the authors show that, at least for computer vision and NLP tasks, you can oftentimes improve model performance just by distilling between two identically parameterized architectures. So you train your model just like you normally would, and then treating that trained model as a teacher, you then retrain your model using both the hard loss from the ground truth labels as well as the distillation loss with respect to the original model. In practice, we found that this works quite well on CVR style architectures as well. However, unlike some CV or NLP models, our models are not static and they need to continuously learn on new data in order to adapt to new ads and to adapt to changes in user behavior. So we need to figure out how to handle incremental model training such that this performance improvement from the train and retrain process, such that that holds over time. Our ads models, like many recommendation models, as I said, they continuously train as new data arrives. So assume for the sake of this talk that each model trains once a day. Then we first train the model on auction winners from day 1. Then we update it on auction winners on day 2, and again on day 3, and so on. So the model is constantly learning on new data and constantly evolving over time. To make this compatible with born-again networks, we organize model training into 2 dependent and parallel model training sequences. First, we have the teacher model. We said that for born-again networks, the teacher is just a regularly trained model. So nothing special here. We train our model and incrementally update it on new data each day, yielding a sequence of teacher models, teacher 1, teacher 2, teacher 3, and so on. Now for the student, we want to train on the ground truth labels from each day and additionally utilize a distillation loss with respect to the teacher. We do this by pairing up the teacher and student such that each day we first update the teacher model on today's data. Then we take yesterday's student and we update it with today's data while utilizing a distillation loss from today's teacher. And then that student model, that's what goes into production in order to serve live traffic. So on day 1, we train our first teacher from scratch, then train our first student from scratch using the distillation loss from the teacher. On day 2, we update our day 1 teacher, and then we update our day 1 student using the day 2 teacher and data from day 2, and so on, updating the teacher, then student, teacher, then student each day. So how well does this work? What's the impact on metrics? Here, I experimented with one of our lower funnel CVR models to compare the behavior of teacher and student models when training with this strategy. The teacher model, again, it's just training normally. It has no awareness of the student. And each day's student depends on a distillation loss from today's teacher in order to help it along. I plotted the relative difference in teacher and student model log loss on the daily evaluation set over a 2-week period. And here you can see that on average, this stage-wise training process has allowed us to produce a student model that's between 0.15% and 0.2% better than the teacher. This is a fairly significant gain for ranking models, and we've observed that this improvement is stable over time. So I've shown 2 weeks of model updates here, but we can see that, or we do see that the student continues to outperform the teacher even after several months. At least in the offline setting, this gives us some evidence that this born-again training strategy can allow us to improve model quality without increasing the model serving costs. But why does it work at all? There are a couple possible explanations that I'll share, though admittedly these are just hypotheses. The first one comes from a 2020 paper called Towards Understanding Ensemble, Knowledge Distillation, and Self-Distillation in Deep Learning. And in this one, the authors analyze these different techniques from a multi-view learning perspective, and they make the claim that self-distillation, it's performing an implicit ensemble and knowledge distillation. That is, by distilling between the teacher and the student model, it's learning all the patterns that it would normally learn from the data, in addition to the patterns that the teacher model had learned. And so that's how you form this implicit ensemble between the teacher and the student. The second explanation comes from the Born Again Networks paper itself, and that is that distillation acts like importance weights to emphasize the easier examples, because the teacher model's predictions, they're just acting like another source of soft labels. Regardless of which explanation you buy into, we do have empirical evidence that this technique can be a pretty effective way to improve CVR model quality. All right. I'd like to zoom out a bit in order to wrap things up. Both of these examples that we've just seen, so model warm-up with distillation or born-again distillation training, neither of these would be possible without having a flexible experimentation framework that makes it possible for engineers to train models in stages, to compose models, and to do this in a way that is straightforward to integrate with incremental model training and updating. At Snap, we found that having such an experimentation framework is really critical to the development velocity of machine learning engineers, and that if you want to have a state-of-the-art model architecture, you need a proportionately sophisticated model training and evaluation platform to support it. Today, I've shown just 2 examples of what ML architectures such a platform can enable, but of course, there are many other ideas that you could try out, such as pre-training embeddings, boosting ensembling, or something we haven't even thought of yet. I'll end things here. We have a bit of time for questions, so if you have any questions on the talk, please let me know and I'll do my best to answer.
Thank you, Joey. That was an insightful presentation on knowledge distillation. We do have a few questions coming in chat, so let's move on to Q&A with Joey. First question, Joey. By doing distillation, do you evaluate a new model offline at all, or do you purely rely on online experimentation?
Yep. So when we're doing distillation, we do evaluate both the teacher and student models. I think this is really important from a debuggability perspective so that you can understand where's the performance improvement coming from, or if the distilled model has a degraded performance, is that because the distillation process itself was a bit tricky, or because the teacher model was not as good as we expected? So we do rely very, very heavily on offline evaluation for both the teacher and the student models separately. As far as online experimentation is always the source of truth for whether these different techniques work, and that is the same for distillation models. So all of our student models, if they are performing well in the offline setting, that performance improvement then needs to be validated by taking the model online in an A/B test.
Thank you. Your next question, does the pre-training strategy make it more difficult for machine learning engineers to reproduce or retrain production models?
My view on that is that it's like no more difficult than retraining a model on a new data set. So as long as you maintain a version history of your models and you have a way to distill from a particular snapshot of your prod model, I don't think you'll run into any additional trouble. You can essentially think of these scores from distillation as an additional column or an additional label that you use when training your models.
Thank you. Your next question, will there be catastrophic forgetting? For instance, after pre-training, you switch to normal training for a few days or weeks. Will the model score distribution go back to the same as just using normal training?
Right. So I think this is in relation to the first section. I had a brief note on this. So we have at least evaluated this up to the 1 month point, and we have observed that the improvement from this pre-training strategy does continue to hold at least after 1 month. And by that improvement, I mean that the model that uses pre-training, it continues to produce the lower predictions on auction participants, the average prediction score that's in line with that of the prod model. And in terms of the improvement on auction winners, that offline improvement holds at least after 1 month as well. So compared to a model that doesn't use pre-training, your model's log loss or AUC, it is still improved at the 1 month mark.
Moving on, how does distillation on auction participants compare to distilling on auction winners?
From what I've observed, distillation on auction winners, it also seems to provide a reasonable performance boost. And I think if you go that route, it's actually somewhat analogous to the born again training strategy, where there you've already trained your prod model as like the teacher, and then you retrain a new model on auction winners using the distillation loss to guide it along. The difference that I've observed between distilling on auction winners and auction participants is that while distilling on auction winners does improve model behavior on those auction winners. So it does improve log loss and AUC. It doesn't directly address the selection bias that occurs between auction participants and auction winners. So your model does still tend to overpredict on auction participants. A very natural extension might be to try to combine the two, though I have not run that experiment yet.
Talking about born-again neural networks, what's the relationship between born-again training method and label smoothing? Have you tried label smoothing instead?
I have not personally tried label smoothing. So as far as like the way that I think about this too, I do think that it's similar, though with label smoothing, you typically have some global amount of smoothing, whereas with this particular training strategy, with born-again training, you have this per instance label smoothing using the teacher to smooth the labels. As it relates to label smoothing on ads models, I haven't seen it applied as frequently to these type of models, and there are a couple reasons I can think of for that. The first one being that label smoothing tends to affect the calibration of your model, since it's changing the average conversion rate in your data. And for our ads models, calibration is a really important property of scores, since the scores are used in the ad auction. And related to that, it is difficult to properly integrate with incremental model training, since the conversion rates in the data, they change over time. So I do think they're quite similar, and in some ways you can think of born-again training as per instance label smoothing, where the smoothing model is continuously updated with new data and at the same cadence as the regular model.
Thank you. We have a couple of questions more. What is the trade-off here between having a higher quality model and the model being more delayed due to multiple training stages?
I think this is going to depend on a lot on your data, but usually for any particular data set, it is reasonably straightforward to quantify. So you can measure what is the impact on model quality if my prod model is stale for, say, 1 day or 2 days, et cetera, just by taking older versions of your prod model and evaluating it on the same data. So what happens if I evaluate my prod model from 1 day ago on today's data? Or what happens if I evaluate my prod model from 2 days or 3 days ago on today's data? And then you can also measure the improvement that you get from this particular training strategy to see like what performance improvement do I get and what's the associated delay with training two models in sequence. And then you can compare the two. My experience for born-again networks is that having a higher model quality, it's typically a more impactful thing to do as long as the delay isn't too long. So born-again training, it might delay the model update by an hour or so. And the improvement in model quality that you get from this training process is going to be significantly greater than the degradation occurred by the delayed model update, at least for the types of models that I have seen.
Thank you. Your final question for the day. Since the production model's data generation is not an unbiased representation of the ad inventory distribution, do you have some type of exploration for generating more unbiased training data?
I think that's a good question. I will partially answer this. So I think this is getting at the fact that's like the auction winners, they're generally selected in a somewhat greedy process. So which ad wins the auction, that's typically the ad that is shown to the user. And you can imagine systems that add some randomness or explicit exploration in the process such that the prod model isn't getting to directly pick which ad wins each time. And there's some randomness to ensure that some of the auction participants end up in the training data for all of the models to see. That's definitely another approach that you can use to trying to align the model scores on auction participants and trying to at least somewhat mitigate the effect of the selection bias that occurs by allowing the prod model to pick which ad wins the auction each time. It's a little bit orthogonal to what we've shown here, but definitely another approach that you can use to counter the same problem.
Thanks again, Joy, for the wonderful presentation and for answering all the questions. This wraps up our last talk for the event. Before we move on to the breakout sessions, I do want to share some remarks as part of closing. With this, we conclude the third annual Ads Modeling and Marketplace workshop this year. This has been yet another successful workshop and second year in a row that we've held this workshop in a virtual setting. I would like to take this opportunity to thank all our presenters, Angadh, Xiaoming, Yipeng, Shobha, Josh, and Joey for their amazing presentations. As Akanksha mentioned earlier, the goal of this workshop is to bring together practitioners and researchers working on ads targeting, ranking, and marketplace design to facilitate knowledge sharing and best practices. This community has grown over the years, and today we have over 500 participants attending the workshop, something we are incredibly proud of. None of this would have been possible without our amazing organizing committee members, who I would like to thank profusely for their efforts. Today we heard from Yipeng and Josh about some of our more recent projects and the progress we've made in this space at Pinterest. If this sounds interesting and exciting to you, please reach out. Please reach out to us. We are hiring for several roles and teams. While the workshop and the talks have come to an end, I don't think the discussion and the engagement has to stop. In order to continue further discussion and engagement on these topics, we've organized a set of 4 parallel breakout sessions on the following exciting topics: DNN modeling for ads, marketplace dynamics and auto bidding, experimentation, and shopping. These breakout sessions involve casual panel-style Q&A with Pinterest employees. I would like to ask all the attendees to stay back and join the breakout sessions of their interest. Last but not the least, we hope to see you again next year in person.